Hey, what's up guys? We're going to look at specific heat capacity. And we use the letter C to represent specific heat capacity. The definition is it's the energy required to raise the temperature of 1 kilogram of material by 1 degree Celsius. And every material has its own specific heat capacity. Here's an example. We've got water. So water has a specific heat capacity of 4,200 joules per kilogram per degree Celsius. What does that mean? That means that if we have 1 kilogram, and we want to heat this water up by 1 degree Celsius, it's going to take 4,200 joules. And every material has its own specific capacity, so it takes different amounts of energy to heat up different materials. So let's have a look at how it scales dependent upon the change in temperature and upon the change in mass that we have. 1 kilogram of water takes 4,200 joules, as we've just seen. Therefore, if we have double the temperature change that we want, it's going to take twice as much energy. So a temperature change of 2 degrees Celsius is going to take 8,400 joules. And 10 degrees is going to take 10 times as much energy, which is 42,000 joules. So energy is proportional to the change in temperature. If you double the temperature change, you're going to double the amount of energy required to heat your material up. Let's have a look at how mass affects it. So if we've got 1 kilogram and it took 4,200 joules for 1 degree Celsius. If we have 2 kilograms, it's going to take twice as much energy. It just makes sense. So that's going to be 8,400 joules. And then if we want to increase the temperature change to 2 degrees, it's going to be twice that, which is 16,800 joules. And then if we want a 10 degree temperature change, that's going to be 10 times as much, which is 84,000 joules. Finally, if we want 10 kilograms of water heated up by 1 degree C, it's going to be 10 times the specific heat capacity, which is 42,000 joules. And then if you wanted a 2 degree change for that mass of water, that's going to be 84,000 joules. And if you wanted 10 kilograms of water to be heated up by 10 degrees Celsius, it's going to take 420,000 joules, or 420 kilojoules. So the energy is not just proportional to the change in temperature, the energy required to heat a substance up is also proportional to the mass. If you double the mass, the amount of energy required to heat it up will also double. Let's look at some real life applications that are explained by understanding specific heat capacity. So as I've mentioned, different substances have different specific heat capacities. So water has a specific heat capacity of 4,200. Sand has a specific heat capacity of 800. And this explains why when you go to a beach, the sand feels really hot, but the water feels cool. Now the sun provides the sand and water with the same amount of energy. It doesn't shine more on the sand and less on the water. It provides them both with the same amount of energy. So you might assume that they'd have the same temperature, but it doesn't happen that way. And that's because water has a specific heat capacity of 4,200 and sand has a specific heat capacity of 800. The specific heat capacity of water is about 5 times greater. Therefore, it takes 5 times as much energy to heat it up by 1 degree Celsius than it does for sand. Therefore, the water heats up slower and the sand heats up much faster. So the sand feels hot and the water feels cool. Now let's have a look at saucepans. In your home, you've got saucepans and they're generally made of stainless steel. But let's have a look at if we were to decide between copper and aluminium, which one would be best? We could look at the specific heat capacity as one of those factors that we might want to consider. Copper has a specific heat capacity of 390 joules per kilogram per degree Celsius, whereas aluminium takes 900 joules per kilogram per degree Celsius. So aluminium takes about 2.3 times as much energy to heat up by 1 degree Celsius for the same mass. And that's not what we want. So we would choose the copper. The copper has a lower specific heat capacity, so it will heat up quicker. The last example is if you want to make a cup of tea, you're going to put water in your kettle. And the one thing that you may have noticed is to heat water from about 20 degrees Celsius to boiling 100 degrees Celsius, it takes a good few minutes. And that's because water has a high specific heat capacity. So it takes a lot of energy to heat up, and therefore it takes a lot of time. So you should always use just the right amount of mass, because the more water you put in your kettle, the longer it's going to take because it will require more energy. Water is really special because it has this really high specific heat capacity, and it's actually really important for life on Earth because it stops the water in the ocean from heating up too quickly or cooling down too quickly, and it actually enabled life to exist. So let's have a look at the equation. We've looked at the proportionality, saying that energy is proportional to mass and the change in temperature. So we can write this as an equation. The energy required to heat up a substance is given by the mass multiplied by the specific heat capacity multiplied by the change in temperature. We measure energy in joules. Mass is always measured in kilograms. Specific heat capacity is in joules per kilogram degree Celsius. And the change in temperature is given by degrees Celsius. So let's write this in terms of symbols and let's look at how we can rearrange this equation. I like to use formula triangles because it stops you from rearranging the equation wrong. So we put energy at the top and we put mass, specific heat capacity and change in temperature at the bottom. The first equation of this is E is equal to mass times specific heat capacity multiplied by the change in temperature. If you want to calculate the mass, you cover with your finger, you cover the M and you get mass is equal to energy divided by brackets. You must put brackets in here else you'll do something wrong on your calculator. Energy divided by specific heat capacity multiplied by change in temperature. If you wanted to determine the specific heat capacity, use your finger and cover up the C and you get energy divided by brackets mass times change in temperature. And if you want the change in temperature in a calculation, you'd cover up delta T, and that gives you E divided by brackets M times by the specific heat capacity. It's really important that whenever you do a calculation, you write your formula first, because that tells you what you have to do. So let's look at a few different examples of how we can actually use this equation. So copper has a specific heat capacity of 387 joules per kilogram per degree Celsius. How much energy is required to heat up 5 kilograms from 20 to 35 degrees Celsius? So we're after energy. So I'm always going to start my equation. E is equal to M times C times delta T. So now we just have to put our values into this equation. The mass was, let's have a look, is 5 kilograms. The specific heat capacity of copper is 387. And the change in temperature. So it's gone from 20 up to 35. So that's a change in temperature of 15 degrees Celsius. And when we calculate that, we get a value of 290,025 joules. So that's how much energy it takes. Sorry, 29,025 joules. I've written that incorrectly. So it's 29,025 joules. There we go, that's better. Which is quite a bit of energy. So let's look at another example. What mass of water is heated if it takes 134,400 joules of energy to heat some water from 20 degrees to 100 degrees? And we've been given the specific heat capacity, which is 4,200 joules per kilogram per degree Celsius. So we want mass this time. So we're going to use the equation for M. So I'm going to cover up M in my formula triangle, and we're going to say that M is equal to E divided by brackets C times delta T. So now we just substitute in our values. So we say that the mass is 134,400 divided by brackets, the specific heat capacity is 4,200, multiplied by the change in temperature. It's gone from 20 to 100, so that's quite simply 80 degrees. And when you put that into your calculator, you'll get a mass of 0.4 kilograms. We always use kilograms in science, but that's equal to 400 grams of water. The next example, we're going to look at how to calculate the specific heat capacity of iron if it takes 180 kilojoules of energy to heat up 20 kilograms of iron from 20 to 40 degrees Celsius. So we're going to cover up C because C is our letter for specific heat capacity. So C is equal to energy divided by brackets M times delta T. I've mentioned before how important those brackets are. Make sure you put them in. So C is equal to the energy, right? This time we've got the energy in kilojoules. So we have to multiply that energy by 1,000 because kilo means 1,000. So that's 180,000 divided by the mass, which is in kilograms already. So it's 20 times by the temperature change. It's gone from 20 to 40. So it's increased by 20 degrees Celsius. And when you stick that into your calculator, you'll get a value of 450 joules per kilogram per degree Celsius, Always remember to give your units whenever you're doing any calculation. And it's that easy. You just put the formula and you substitute your values in. So in summary, what is specific heat capacity? It's the energy required to raise the temperature of 1 kilogram of a material by 1 degree Celsius. And different materials have different specific heat capacities. The higher the specific heat capacity, the longer it takes to heat up because it requires more energy. And if it's got a lower specific heat capacity, it heats up much quicker. The formula is energy is equal to mass times specific heat capacity multiplied by the change in temperature. And it's really important to remember your formula triangle and how to rearrange your equations. That's it. Thanks for listening. See you all soon.